Welcome to Study Loop.
Problem 41.44, we're told about some properties of the gate of a silicon-based MOSFET, a particular specimen of one. And the first thing we want to know is what is the capacitance from the gate that has a silicon dioxide layer separating an electrode from a p-type semiconductor. And so the p-type semiconductor acts as one plate, and then the electrode acts as the other. And then we want to say what the charge is in elementary charges on the plate or on the gate or whatever when the voltage is a certain value. We'll get to that momentarily. So we know that for a capacitor, that its value is permittivity, which is the dielectric constant times epsilon naught times its area divided by the separation. So we're told a few things. We're told that the gate is square and is 0.5 microns on the edges. So 0.5 microns squared is the gate area. And then we're told that the thickness of the insulating layer made out of silicon dioxide is 0.2 microns thick, and that its dielectric constant is 4.5. So putting these numbers in here, we find that the capacitance is 5 times 10 to the negative 17th farads, which is quite small. Usually when you intentionally have capacitances in a circuit, they're in the picofarads, about the smallest that you're going to use, which would be the 10 to negative 12th to the negative 12th range. So this is like 5 orders of magnitude smaller than capacitances you intentionally put into circuits, which is good because if you recall back from the circuit stuff, if you have a resistance and a capacitance, then it takes some time to charge the capacitor up. And if you're wanting this MOSFET for like doing digital logic in a computer or something, you don't want it to take very long for it to charge up, because that makes it take longer for the transistor to turn on and off, and it makes the your computer or whatever slower. So then in part B, we want the number of elementary charges that appear at the gate when we have a gate source voltage of 1 volt. So we know that the charge is equal to the capacitance times the voltage. And if we call n our number of elementary charges, then the total charge is just the number of elementary charges times an elementary charge. So this implies that n is equal to c, which we know, v, which we're given, over e, which we know. And this is 3.1 times 10 squared. So there's only about 300 electrons on the plate of this capacitor when it's got a potential difference of 1 volt across it.